Alright, dear good evening, students. We are back to the DAE lecture. Now it's still we're on the fourth lecture, third issue today. Still we are about linear DAEs with variable coefficients. So variable meant that this E and this A matrix that they were depending on time t. So we're continuing here. Before that we had equivalences. So what can we mean by equivalences of such pairs of matrix functions? And then last lecture we had this local canonical form, which were giving us these characteristic quantities, as there were notably the R, which was the rank, there was this A, which was the denoting the algebraic part, and there was this S, and this was the strangeness. This was algebraic part, and this was the rank of the E matrix of the current. And today what we're going to see are that those characteristic quantities, they will be functions depending on time, like the matrices. So they will be time varying, these quantities. But we will start with an assumption that this is basically constant, although they change. They may change in time because they're also integer. That means a change will always mean a jump, and well, we will argue that it makes sense to assume that they are constant over time. Then we will talk about a global canonical form based on this assumption that these matrices have constant rank. And from that we will go in and eliminate the strangeness in an iterative process. Alright. Yes, they're running. Okay, then well, let's start right here. So once more, last lecture we were considering just matrices. So these pairs of matrix, E and A are matrix each. And we had with this local canonical form, we found that we have these characteristic values. Like there was this R, the rank of the matrix, there was this A, which were denoting the algebraic part, and there was this S, the strangeness, and all others. There was still a D, and there was a U and a V, but they were all defined in terms of R, A, and S and the dimension of these matrices. And now what we will see is that for matrix functions, so we have, say, E of t, then certainly the rank will be depending on t. So if the matrix changes with the time, then the rank may change. And well, since the rank is always an integer, means if it changes, then it will make a jump. But similarly, of course, the A will be a time-depending function, but also the S will be a time-dependent function. Will depend on t for pairs of matrix functions. Now, really the important thing here is these matrix functions. Okay, well, and then we start with this assumption that we will assumption will be that these quantities, so assumption will be that R of t is actually constant equal to some R, A of t will be constantly equal to some A fixed value, and the same with S. T will also be, so generally it will be a function of time, but we will assume this to be constant. Well, in the script I have a number of reasons why this makes a lot of sense. Well, maybe one example, what can happen. So if you think of a circuit like we had it before, I think it was looking like this were our easy circuit equations. Well, and then you may think of having something like a switch, and then there is another circuit connected to here. Maybe another, this condensator and a damper, and here there is a switch. Maybe at some certain t star, the switch will close, and well, and that is such a point where such a rank will change in the matrices, where the model itself changes. Of course, that makes the power out of DAEs, and also what makes it so difficult to analyze in the very general case. But on the other hand, so you will know when you push the button here such that the switch is activated. So these are like random events, and this is also an assumption why it may. This also justifies that one may well assume that these rank, for example, can be constant, and this then transfers to these other quantities. And there's also a very general result on that. If the matrix functions are smooth, then there can only be a finite number of jumps. So this also makes this justifiable. And if you really want to consider DAEs where these quantities change in time, then the idea is piecewise. So consider time intervals where these quantities are piecewise considerations. So consider time intervals where these quantities are in fact constant. Alright, and we start done with a theorem that bases a lot on this on this assumption of the piecewise constant. Namely, so we assume that we have given such a matrix function, E depending on time, and then we assume that rank E is constant over this whole interval, and this means then there exists U, which is of the same smoothness, which will map into ECM, and V in also the same smoothness. This will map to the n times n. These functions are pointwise unitary. Unitary means, just to remember this, unitary if and only if UHU is the identity, meaning orthogonal in the complex sense, and this in particular implies that U invertible. So every unitary matrix has this inverse, so it's invertible. So these U and V are pointwise invertible, and they have this nice property that if you apply this UH to the E and then the V from the right, you will get the matrix as you have. I hope you notice from singular value decomposition. That's a singular value decomposition. Here are the singular vectors, you apply them, and then you get this diagonal matrix. Here the sigma that has the singular values on the diagonal. But the point is that these singular values, so the E changes in time, then of course singular values will change in time. And really the interesting fact of this theorem is that these U and the V, they are also functions that are smooth, and also the singular vectors, they are smooth functions. Meaning now that, well, you can, already thinking of transforming the DAEs, you can apply this from the left, and this is a state transformation then. It's differentiable, so we can later have this dot here. And then we get this E in this form, where here is basically the identity. It's a diagonal matrix. We can do another inversion. Yeah, and well, here that's the fact of the theorem, that all these are smooth functions that realize this singular value decomposition for a time-dependent matrix. Okay, and this result, that's in the book by Kunkel and Merman, Theorem 3.9. This will be the key to then next proving the global canonical form. So Theorem 4.3, the global canonical form. Or you can also call them the global characteristic values. Yeah, you will see. So let's have E and A to be a matrix function, sufficiently smooth. Yeah. I guess that, well, let's just assume that they are differentiable. I think we can discuss about the A. Maybe there is less differentiability needed. Alright. But what we have to assume is that these A of t is a constant over time, that these R of t, basically the rank of E, is constant over the time. And then also these S is a constant value over the time. But this, well, these are not yet global characteristic values, because, yeah, these are defined as the local characteristic values. Meaning that whenever we have a time, then we have the E matrix and the A matrix, and then of course we can compute these local characteristic values. And for now we assume that that they are constant, and they will be then later global characteristic values. But for now we just set this like this, and then we assume that they are constant. Still we have to prove that they are somewhat invariant under these equivalence transformations that we consider. And this is namely then says the theorem. So if these local characteristic values, if they are constant, then we can find transformations, no global equivalence of this EA towards these matrices. And well, here you again see these as the D. Of course, this is the rank here altogether. Here's this A again, as we had this in the local matrices. And then we can talk about that these are global characteristic values, because every E and A is equivalent to this form. And that then means that these S, A, and D, that they are characteristic values also under global equivalence transformations. And what we have to say is that these Aij matrices, so these block matrices that appear here, that they are also then matrix functions. They will depend on time. Alright, and this here is the U block. So this block has size E, and this is, how do we calculate this? N minus S minus D minus A, where D was R minus S. Okay, never mind. Alright, that's the theorem, and now let's look for the proof. What this looks like, basically there are two ingredients in the proof. One thing is the continuous SVD, that, for example, let's already look at this block here. That becomes best obvious. Oh, we can also look at this. Which one do we take? Okay. For example, we had this A22 block later on here. This will be this A22 block. Then we know that there will be a U1H and the V1 from this side, and then this will be actually this will be this matrix here, as we had it in the theorem before. But of course we can do another scaling either here or there, so that we have an identity here. Size A, this will be this part, and this is the one thing, and the other is elimination of blocks. So where do we see this best? Yeah, for example, here's this IS block, and what one then does is, well, eliminating using this line, all going up here. This is something we can do from the left. That doesn't make any problems. No. All right. So just to tell you what are the two operations that we're going to do. One is this continuous SVD. The other one is using these blocks to eliminate other blocks. But let's go through it step by step. How does this work now? First thing that we do is SVD of the E matrix, as we had it before. So this will be left, right, and then of course there will be the V dot needed, but that's already in here included. So this matrix is already the that's already the U H A V minus the U H E V dot. That's all included, and that's another issue, a point of this proof, that A1, 2, and so on will change over over the steps, meaning we don't care too much what it actually looks like, the A12. So from here to here we still use A21, but they might be different matrices. Okay, so here, this what we see here, this already is what comes out from the global equivalence transformation of this E matrix towards this SVD form. And then here, well, this also induces a block structure for the A. And then next thing will be multiplying by this matrix, actually sigma to the -1 identity. This will make this identity, and here you see that, well, actually here that's not the same as here, but it doesn't matter. Just there are some matrices in here. Okay, and that's how we get from here to here. Then next thing what we do is this A22 block. We want to put this, extract the invertible part, so to say. So we want to have those apply a transformation such that it looks like this. What we need is from the left U1H, and then this of course will affect this whole line. And from the right we will meet this V1 matrix. This will then also affect all of that. And well, but this also means that we need to consider this actually was V1. This was its transformation, and we need a dot on that, and this will become the 0. So we need to, this is this time dependent part that we have to add with the e, and in this case it's 0, so we don't get anything else from here. But this transformation makes that this part here is condensed towards this identity of A and here the 0. And then same thing happens with this A31 block, which is still here. Here again we apply UH in the bottom line, and then we have to, well, in the first row, in the first column, we have to apply this V2 from the left, and in this case we will get a contribution out of here, but this then just sums into this A11 matrix here, which is generic anyways. And with that we have like identified these blocks here, the IA block and the IS block. Then we can, well, use this IS block to eliminate all the blocks that were before here, and since there are only zeros in here, nothing changes so much. Now we will use this AI block to eliminate here, and then that we will get multiples of this line multiplied to there. But again, this doesn't matter because these are generic values in here. And that brings us to in this formula. So we have eliminated all blocks that we can just eliminate. We can go even further and take the IA to eliminate those blocks here. That's how we get these zeros. Okay, and then what happens now? Okay, now that's maybe a trick that so what happens here is basically a multiplication of the second row by q. Then here we get the q, and here we get these identity q dot, the part that comes from the E matrix with the dot in here. Why do we do that? Because now we can, well, choose this q2 exactly such that this equation is fulfilled. So we choose q2 as the solution of q2 dot a22 q2, and q2 of t0 is the identity. Then one knows from ODE theory that q2 will be always invertible, and then this in particular means that this block here, this will become 0. And that's basically a way how one can use like the differential blocks to also eliminate here things. Okay, by that we have arrived at this canonical form by all these, and then as we did it in the proofs before, then one has to sum up actually all these transformations that have happened in between, and then one can read off that these are the product of all these transformations, that they sum up, that they multiply up to one transformation that makes this global equivalence transformations. Okay, and with that, this is proven. And the last thing that we now do is, so we have transformed this DAE into this form. What we are going to do now is looking at the DAE that is the result out of these transformations, and then we do some observations on that. And yeah, and then the final step, I will show you how we eliminate the strangeness. What was the strangeness again? If we look at, let me write down the DAE for this part, and then strangeness will become very obvious. So what does the DAE now look like? Here the first line, this will give us x1 dot as a12 x2 plus a14 x4 plus a right hand side. Second line gives us x2 dot as just a24 x4 plus a right hand side probably, and the next line just gives us 0 is x3 plus f3. Okay, so that's the algebraic part, that's very well visible. And now comes the strange part again. 0 is x1 plus f4, and the last equation is 0 is the same as f5. Okay, now looking at that, for the x4, we actually see, okay, it's a bad matter of from what angle you look at it, but it will turn out that x4, they just appear here like in the right hand side, so they can seem somehow to be chosen arbitrarily. There are the free variables, free or undetermined variables. Maybe best seeing, well, if you have like this equation, then every of these variables can be the free variables, but we will see that these x4 is in fact those that like can be chosen freely. They are not fixed by anything else. Maybe this is the easiest equation here, that the 0 is f5, that's the redundant part. Of course, f0 then should be 5, otherwise there will be no solution, but that does not define any variables, that's so to say redundant part or the vanishing. Part. Okay, looks like it's going to be late for the computer, but I hope we make it to the end. Now x2, look at that here, that looks like an ODE. Oh, we have x dot is, we said x4 is the free variables on the f2. However, they are coupled to x1, and x1 is the strange part. Here one may think, okay, it's easy, x1 is just the same as minus f4. But then we also see that we also have this x1 dot is something else. So this is the strange part, as we determined last week, the variables that are given algebraically and through a differential relation. And that's the crucial point here. So let me make this. However, and this is about the x2. They are coupled to x1, strange variables. And in fact, we will see that they play a major role in here, because what we actually can do is, so this is now eliminating differentiating and eliminating the strangeness. If we take this equation here, so let's give this 1 star, and then we will later use this equation, so we give it 2 stars, and then, well, this will make up the final DAE. So in fact we could differentiate this equation, then we get that dot here and the dot here. Then we see that x1 dot here, so we can replace that x1 dot, eliminate this x1 dot from here, replace it by f minus f4 dot, and then what we will get is a DAE for the x2 part. It used to be an ODE part but coupled, and this will be then very nice DAE for the x2 part. Okay, let me differentiate and eliminate will give us differentiate this one and eliminate in the double star will give us minus f4 dot as a1 to x2 plus a1 for x4 plus f1. Well, then to see this better, we will immediately put this on the other side. Move all this. 0 plus f4 dot. But we still have this other equation for the x2. So we will have x2 dot as the same as a24 x4 plus f2. But well, this is a DAE. I hope you can see this. Well, let's write this with this EA part. So here we have the 0 identity. x2 dot is a1 to 0 x2 plus, well, some right hand side. So this in fact is a DAE, and well, and then one has to repeat all these things. In particular, this is depending on time. So this is again a time varying linear DAE, meaning, well, one hasn't maybe gained too much out of that, but one can do the same process again, and that we will see next lecture that this is a well-defined process which will stop at some point of time. But until we get to that, let me, I guess, the final thing, what does this differentiate and eliminate process mean? This basically means we take so we had this EA to be equivalent to, write this here, this one, to this IS ID matrix, and some zeros here, and here we had this 0 IS. Okay, let me put all the zeros here. Okay, maybe forget about the last a1 to 0, a1 4, 0 0, a2 4, 0 0. Okay, and this 0 we also have. Okay, don't be lazy. So we had that this is equivalent to this form here. This was the global canonical form, and now with these differentiate plus eliminate, we put this into another form that now looks like what has happened? We have replaced this here. So this is gone. Here we will have just a 0. But in fact, instead, now we have the x2. Oh, we had it before. Okay. Well, basically only this one is gone. 0, 0, 0. ID 0, 0, 0, 0, 0. Zero, 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 0. 1, 2, 0, 0, 0. 0, 0, IA 0, 0. And these are the blocks. 4, 0, 0, 0. And well, by differentiation we could eliminate this block in here. Now, well, this again, this will be like the E tilde, or this will be our E1 and the A1. That again is a DAE, but what we mostly gained is that this part is like smaller now. Before that we had like a huge part in the E, and now it's shrink to this one. And if this will be 0 at one point, or maybe the S part is gone before, then yeah, we will be done. But that's then the next lecture. For today, what is important is that we can put this DAE into this global canonical form, and then we can do differentiation and elimination to get another form, which has less strangeness, or maybe which has less rank in the E, and then since the rank will be smaller, getting smaller and smaller depending on the S, this has to terminate at one point of time, because either there's no rank left in here or the S is 0, so we will not make this smaller anymore. Okay, but that we will look on next week, since we also have the exercise. All right.